Thank you for the introduction, and thank you actually for inviting me here today. My name is Wahib. I work here actually in this building. Traditionally, I come from background of AI. That is my PhD, but then I moved to HPC because AI was kind of like in its winter when I graduated, so HPC was more interesting. And then it's a full circle where I went back to also try to work at the border of HPC and AI. So the talk will be focused also more from the perspective of high-performance computing. Today is an introduction to AI. The aim of this talk is you are maybe witnessing an opportunity that generation before you or after you might not get. That is, could be a once-in-a-lifetime event where a lot of yes, sorry.
Can you be a little bit louder?
Yes. Yes, do you hear me in the back? Okay, sorry. Okay, so again, a lot of the areas you work in different fields of science or engineering might be reshaped by what's going to have forward. Again, of course, machine learning at the end of the day is just a tool to do things, but I think it can play a very big role in that. It's kind of similar to how actually many disciplines in science were reshaped when computers came to existence, right? Not all sciences are computational sciences for sure, but there are a lot of sciences that were reshaped by computing. So a lot of modern day numerical, computational biology, computational chemistry, computational physics, and engineering was reshaped by computers when it came out. So it could be an opportunity for something like that. Finally, the aim of this talk is not to give information. I actually suspect that probably in an hour and a half, it's not enough to learn a lot. But the main aim, or what I hope you walk with, is actually to motivate you to, on your own, go and find out more. So outline, this is split into three chapters or sections. First is talking at a high level about what is AI and machine learning, and then a small introduction to LLMs. LLMs is just one of the tools available in machine learning. It's not the only thing. But that being said, because I'm sure you might have, or I thought you might have questions or interest to know how LLMs work, because it's widely used. So I thought to dedicate a chapter. And finally, some examples, motivation examples of how the use of AI in different scientific fields allows you to do a lot of things. First, AI and machine learning. What is machine learning? It's basically a field of computer science that gives a computer the ability to learn without being explicitly programmed. It's a very data-driven approach, right? That is, you have a lot of data. From this data, you are able actually to learn. You don't explicitly tell the model how to follow rules. A good example is if you teach a model to play chess. One way is to teach the model the rules of chess. Another way, which is machine learning, which is a data-driven or model-based approach, is to not, teach it chess, just show it a lot of chess games, and then you hope the model from seeing that it learns a pattern. So it's about pattern learning, okay? And then you can make a lot of predictions. There are different types of learning. You can broadly divide them into three categories. Supervised, that is, you give a model data that is labeled. Right? For example, you give it an image of a cat and it has a label next to it that says cat. So the model knows what is. You're labeling that. It's called supervised learning. It's widely used. There's something called unsupervised. That is, you give the model the data and you don't label or guide it, and you let the model learn on its own. A very famous example is clustering. That is, if you give some documents or so on, and you let the model cluster or group them on its own without you telling it how to cluster. Finally, something is called reinforcement learning. That is, you allow the model to choose from a set of actions, and this action gives you reward. And from the model exploring this space of action, the model on its own learning. It's widely used in gaming, for example, right? Where you can say, I want to teach a computer to play Mario. The only actions you have in Mario are 3 actions, actually, 4 actions. You can move forward, you can move backward, you can jump, and you can throw items. And then the model, every single time it's taking an action, deciding in every step to take an action, there is a reward. The reward here can be items you collect, or score you collect, or dying, which is a negative, it's a penalty. These are broadly the 3 types of learning, database learning, so machine learning you can use. What is deep learning? Deep learning is basically a subset of machine learning. Machine learning is a whole long list of tools and methods. right? In which there's a representation or a way where you can map an input to an output to an input. The word deep means several layers. Think of it, they are composing. It's like a nested set of functions, one after the other, usually represented in the form of a network. And that's why they call it a neural network. It takes inspiration from the human brain. But in fact, that's just an inspiration. What it is just basically a set of mathematical functions, one after the other, or one enclosed in the other, like this. And deep learning is a subset of machine learning. So you have AI, right? And within AI, there's a subset of AI called machine learning, in which you learn by data, right? From seeing data. And there's 3 ways to do it: supervised, unsupervised, and reinforcement learning. And then deep learning, which is another subset of machine learning. So you would ask, why is deep learning useful, right? Well, the reason it's useful is it's easy to adapt, it's flexible, and it's end-to-end, right? So I can train a model to do many things in deep learning, and it can be adaptable and generalized. And this is a desirable property, right? But why does it work, right? Why can I, giving some input, map it to some output, which is very important, actually. Like, think of it in any field you work in, like, computational biology or engineering or life science or physics. A lot of the underlying phenomena you want to understand is cause and effect, or input and output. And you're trying to reverse engineer nature to understand how something works. From an input, you get an output, right? And what a neural network does, or a deep neural network, it allows you to map any input to any output. You teach the model, you show the model enough examples of input-output pairs, and then without you knowing the actual underlying mechanism or function that maps the input to the output, the model can just predict, which is very excellent, right? And there is work called universality theorem that shows mathematically, in principle, if you have at least some model, it can map any input to any output. The question is always, what does it look like? And that is when it becomes a boring part. You don't probably have to focus on. But there is very different ways where you can map a neural network. It can be thin, it can be tall, it can be shallow, it can be deep, right? It can be the same number of parameters. And number of parameters is some very important thing, right? A number of parameters in a model is an indication of the capacity of model to learn. You want the model to learn more, you increase number of parameters. It's an oversimplification, but you can always think of it this way. You're learning something so complex, you have a lot of training examples, you need a larger model. You learn something that has few training examples and is simple, you need a smaller model, right? How can you increase the parameters? You can make the width of this increase, or you can make it more deep. You just increase number of parameters. And as your input gets mapped to the output, your input is flowing through all these parameters to get to your output. Which one is better? I mean, there's a lot of arguments on that. There's an important part though. Like I said, this can map any input to any output, whatever the dimensionality is, right? So for instance, if I train a model enough, I decide to say, I want to predict the likelihood or predict what is your expected, say in this school, right? Let's say I want to predict, I don't know, the outcome of this school. Who are the students that perform the best? Give some score. I define something called a score, right? And I want to give it some inputs. I don't know, maybe your degrees, number of papers you published, your specialty, your previous scores and previous, your history in exams. I just wanted to spit out something I rank with. You can do that. The model can learn any input-output pair after all, especially in non-linear relations, which is complex. Linear relations are easy, right? Non-linear are very complex. We said it's actually usually universal, right? That can map anything. The issue with that is this universal law of approximation. It gives you a bound on the approximation error. It tells you that in this process, there's some approximation happening. It's not really exact, right? So there is some error in it, but it's bounded. That means in principle, you can always learn map and input to an output. That being said, there are other sources of errors. Something called generalization error. What does it mean? That is, I showed the model training examples. So I showed the model the scores, and again, some numbers about the students in this room. But tomorrow morning, I have a new student that comes, the model didn't see before. Can the model predict for that student? Sometimes, but sometimes it's not So there's a margin of error there, which called generalization error. And there's something called the optimization error. This relates to the internals of how this works. So in practice, you don't see a simple neural network doing everything. You have something called inductive bias. That is, you build into the model design certain elements to extract the pattern. At the end of the day, neural networks are nothing but sophisticated pattern recognizer. There is a pattern, and you want to learn the underlying pattern. That's it. It's not, I mean, people like to mention big things like intelligence, and even the word AI, artificial intelligence. There's intelligence, there's artificial general intelligence, there's super intelligence, there's brain, and neural network, it implies it has something to do with the brain. It's nothing about that. It's just very sophisticated pattern recognitions. Very, like, hard to find patterns that sometimes is not obvious, sometimes very complex, non-linear patterns, right, that you want to find. They are very useful in finding that. That being said, if you use always the same style of neural network, people in practice, not in theory, found it to not perform very well, right? So over time, people came up with innovations in how they design the models, right? Models are adapted for which was called inductive bias, right? They have better capability based on the pattern you have. So let's say the pattern in your data you want to learn. And by the way, what defines the pattern? It's your goal, right? What do you want to extract from this pattern? If you are, a biologist or a chemist or a physicist or engineer or computer scientist or mathematician, and you have some data and you suspect there's some pattern that if you understand it will help you explain the underlying phenomenon you're interested in learning, right? If it happens that the pattern is spatially local pattern, there's local, spatial aspects, then people figured out something called a convolutional neural network, which is still a neural network but has certain design, is much better in that. A good example of spatially local pattern is when you want to recognize something in a picture, right? If you have a photo, this photo of humans, we humans tend to have all our spatial features, like all our features in a spatially small place. So if you have a photo of yourself, your head, your eyes, your ears and nose are all usually spatially very local. They're not spread out in the image, right? So you want to extract features to recognize a face. They're usually very local. People figure it out. If the data you want to need is temporal, and I guess a lot of you might run into that. If you're doing, for example, weather prediction, you're predicting in time, in the future. So given the weather now and given the past patterns, we know what will the weather look like in 3 hours or 12 hours, right? Good example, if you're trying to predict, time series or, stock price or whatever it is, there is usually some temporal pattern. So if the underlying phenomenon you want to understand as a scientist includes a temporal pattern, a pattern that evolves over time. It's very common, by the way. People develop something called recurrent neural network, right? If what you have or the pattern is about structural relationships, so if your goal was to understand, you're a social scientist and you want to understand the impact of how, viral videos or news propagate between people, you can always represent these people connected in a graph, where each node in that graph is one person and each edge means, you know the person or you're transferring to them or you can send them a message. Just some communication link between us. If the underlying pattern is structural, then people develop something called graph neural network. If what you want to learn is a pairwise pattern, so you have a lot of data, and this data you need to understand pairwise, right? So if you have a lot of elements, and each element might affect the other elements, but get affected by every other element at the same time. A good example for that is language, right? When you write a sentence in any language, each word can have an effect or affect the semantics of every other word, right? Not necessarily in the same level, right? But it might have an effect, depends on the semantics, the language, the grammar, and vice versa. Every other word in the sentence before me and after me might affect the meaning of my word. And this is where people invented what's called self-attention, which is part of transformers, which is basically the main underlying architecture of LLMs, large language models. Right? And etc. This is not the only types of, ways where people develop sophisticated elements to add neural network to learn from data. So the important part to learn, to take away from this slide is, at the end of the day, what modern machine learning, in particular deep neural networks, can do, they're very effective in extracting patterns or recognizing patterns if you have a lot of data, a lot of high quality data. Right? I think this matters. Having a small amount of data or a data that is not very high in quality, like has a lot of repetition and redundancy or measurement error, the models are not going to learn well. If you have a lot of data, it's high quality, then what you do is you understand, okay, in what I'm trying to understand, there is some pattern. Based on the pattern, there's many ways where models can look different. So I will switch back here to just a simple example. That is, I will basically go to, if I want to have a spatially local pattern, just as a motivating example for you. Right? At some point, I'll switch to the more complex architectures. But for the time being, let's focus on something simple. If you're very aim, and by the way, when deep neural networks or convolutional neural networks were invented in the 80s, this was in fact the motivational case. That is, you want to recognize handwriting. To be specific, they wanted to, those banks that want to have people, sign checks. There's something called checks. Maybe people here in the room have not seen them in their life. It's something that's, I think people stopped using checks. It was a way where you can, pay some other person or, financial transaction, sign a piece of check and say, I will give this person X amount of money, to his name. And then the person can take this check, go to the bank, and then cash it, right? So that means people can, on these checks, write numbers. Like, I want to give you, $100. Usually you had a human recognize this, and then people thought, can we recognize this in an automated way so it's become more efficient, so you can process more checks. So this was a very motivating case, by the way, a real-world motivating case, 1980s. One way you can think of it is that, well, if there's a number, let's say if I have the person write a number in each rectangle, right? You can always take that number and just represent it as a picture made of pixels. Pixels are picture elements. You can think of any photo. I discretize it into small points like this. Each one is called a pixel. And then I assign different colors in these squares if there's a number. So the number 2, while when you write it looks nice and clean, I can internally represent it in a digitized way, right? This way. Not something as simple. So one way to view this problem, how would I recognize, is I want this to be given to some machine learning model, and it recognizes, tells me that this is number 2 or this is number 6. Okay? So here, what is a mapping? Remember I told you a machine learning model or neural network, to be specific actually, can map any input to any output. So all you need to do is to think, how can I map the input to the output? What would be the input here? Simple. All these pixels. So if this is, 16 by 16, I think, right? So you have the input is of dimension 16 by 16, but the output is just a number, right? How many numbers can you predict? 9 numbers actually. 1, 2, 3, 4, 5, 6, and 8, 9, and 0. So you're mapping from 16 to 16 values to classifying. This is called classification. You want the model to predict the output among one of 10 possible values. Right? So one way to think about it, you can say, okay, as a model, I will give it the input every single point here. So you have 256 values, right? And the value is easy, actually. It's 0 or 1. Either this is empty, it's not part of the number, there's no ink, basically. If you imagine that this is ink you're applying to a piece of paper that you then represent it this way, it's a 0, or it's a 1 if there's ink. So you have a vector of 256 values. Each one of them has a value of 0 or 1. Now you're good. So you have an input here. And then the output is what? Like we said, it's easy. We said whatever you predict, assuming what's written is actually a number, right? I would not take a letter, for example. You cannot write C or Z or something. Then the possible value is 1 out of 10. And, right? So each number here, you can always say, I'll make it just binary. Only the number, if the number is correct, give me 1, the rest are 0. Right? That is, if this is 2, then the output coming from here is 1, like it's correct, so it's true or false. The rest are false. And the reality of, because we said the internal model, which I would explain, is It has approximation errors, generalization errors. So usually you don't assign to it just an exact value. You assign a probability, basically, confidence. So think of it, you assign different probabilities. They should add up to 1, right? All of them. So this is 1, this is 2, and so on, right? And you assign, probabilities here that they add up to 1. So 0.7 means 70% probability, 0.1 means 10% probability, and so on, right? And you pick up the one with the highest probability. So the model, what you want from the model is, I want to give it any image. That image is basically flattened out as pixels. Those pixels are represented in just one line of the values. And I want it to give me the probability of what is the number inside this picture, right? And so effectively, you're mapping between these spaces from 256 variables to 10, right? And in deep learning, this function here, this box here, that you want to give it the input and map the output is basically the neural network, right? Now, how would it look like? Think of it that you're always multiplying some inputs by weights. And you add something called bias. You spit out the output. It's very easy. It's like weighted average. Like you're assigning weight to each parameter, right? And this is where the model is basically trying to learn. These parameters are capturing all the learning that's happening. So a simple way to look at it is you assume, remember our example? It had the inputs. In our case, it was 256. The output is 10. And you add layers as much as you want. How many do you need? Well, the rule of thumb is the total number of parameters. And by the way, each one of those lines here is a parameter. Should be the ratio of number of training examples to parameters 10 to 1. You have more training examples, you increase the model. How can you increase? You can just make each one of those longer, or you increase more layers, right? There's a lot of theory and also empirical studies on the ideal composition of this model. But at the end of the day, it's mostly empirical, and we do know that certain settings, certain sizes work. So the example of neural network is that the data flows. Whatever your input is, in our case it was just the value of a pixel and an image, is flowing through this network. And it goes forward like this, right? I can skip this highly technical part. In fact, it might bore you, right? But I will share the slides, so all this is available for just completeness. I'll give you just the important part, sorry. Right? That think of it that the output of starting from your input to your output, you're going through stages where at each step your input generates some output, and the output of the first layer is an input to the next layer. So that's why you draw in brackets like this. The very most internal one is the last one, basically, right? Because the input to that is the output to the next. Sorry, the very inner one is the first one. So you're computing the first layer here, which is inside this small bracket. Whatever comes as output goes as input to the next layer, and so on and so on. So it's mathematically quite easy actually to represent this structure. So what you want at the end of the day is for all these 256 values, you either have ink or you don't have ink, and you're flowing this, through this model. And you want basically as an input, right? To know and let the neural network, learn on its own from seeing these examples and adjusting the internal weights, how to predict correctly, right? So this is, I'm telling so far, it's called supervised learning. That is, you will show training examples to the model, right? That is, I will show it actual, images of people who wrote numbers. And as a human, some human sat down and said, what is the real ground truth of that? This is 5, this is 0, this is 4, this is what? It's called supervised learning, right? Why would I need that? Because I need the model to know ground truths. Because when the model is in a training stage, it keeps on predicting. Initially, it corrects, might predict wrong numbers, but then I needed to predict the correct numbers. And neural network is basically going to find the ideal parameters to get you the highest prediction, right? So effectively, each time you give an input, the model predicts. You measure the distance here, the cost. Is it correct or not? Is my prediction, so I give it here, this one. This is, say, a number 1, for instance. And the model predicts. But for some reason, it just the model is predicting by mistake that the high, this is number 9, for example, with a very high probability. That's wrong. So I want to change the model weights such that next time it predicts in a correct way, right? And you have to repeat that for every training data set. So for each training example, you compute what the term is called loss, right? There's a loss function. Loss function means the distance or the difference between the prediction and the ground truth. If you predict exactly correct, that's perfect. If you don't, I measure how far your prediction was from the ground truth, and then I need to adjust this model parameters inside the neural network to make sure in the future it does correctly. And this is what's called training. You're doing training of the model, right? Again, skip this part. I assume a big amount when I check in the room are from fields of like computational, life science, computational biology and chemistry and so on. So for completeness, there's full details if you're a computer scientist or a mathematician or physical scientist who want to learn more. But to not bore people with details you might not need, I will just skip this part. And again, I will be around if you need to know more details about this. I'll be glad to explain. And that part I can skip. Okay. In real life, unless you're actually some person who's developing AI technology on your own, right? You will probably not have to see or interact with anything I have said so far. Usually there are frameworks like say PyTorch or TensorFlow or other frameworks at which if you are training models, your job is mostly to define what the neural network looks like, prepare the dataset, training dataset, and train the model, right? And all the mathematical part internally of, as I said, the outputs become inputs, and how you propagate, how you measure the loss, how you back propagate is very hidden from you. You're just calling functions to do that, or APIs. So unless you're developing technology that is directly AI technology or optimizing AI, you will not be seeing any of what I said, right? You're usually using, again, a high level here, which does for you all that work, right? Again, an important part to walk with because you can even know what the model looks like I mentioned earlier. You might design a model that the model on its own has design elements to capture the pattern better. Sometimes you don't. You just pick a model people before you know and develop, and you just train it on new data. Or you do fine tuning, that is, a model is already trained and you just make it more tuned to your data set, right? But it's important to know how much training examples versus a model weight I know. And again, the rule of thumb is 5 to 10 times the number of model weights. Here's where I switch a little bit into LLMs in specific. Like I mentioned, it's among one of the tools. I just want you to recognize, because I mean, there's a lot of hype that is, LLMs is the future. It can do everything. Anything a human can do, it can do, etc., etc. So it's important to distinguish hype from real prospect, right? That being said, this is not specific to machine learning or LLMs or AI, right? Throughout human history, every time a very foundational technology or emerging technology appeared, right, there was a lot of hype around it. And the reality is, after the hype cools down, the real value appears. There's a nice article here. I found it very amusing. It's an old article that's trying to understand what happened when X-rays was first invented. Again, of course, X-ray is a transformative technology, right? But when it was emerging, people don't understand it very well. There were all kind of hype around it. And I'll just have, from this article, if you have time to check it, it's interesting. There were all kind of weird products being sold in the market. Like X-ray soup, right? You buy soap that has X-ray in it. People don't know what X-ray is, but just because you have X-ray written here, people say, oh, it's just good for you, right? X-ray whiskey, right? Well, I don't know what that is, but it's X-ray whiskey, right? There was X-ray stove polish. There's X-ray, I don't know, matches maybe, right? X-ray razor blades, right, to shave your beard, right? Those are real things. People were paying money for that, right? There's X-ray headache tablets. You have headache, right? Just take X-ray tablets and you're good to go. And the best of all, there's X-ray exposure. Yeah, you go to a clinic and you have headache, and oh my God, you can see the guy having headache here, right? And give me a dose. right? And they apply X-ray on you exactly, and that solves your problem, and you go away healthy, right? Which is I find very amusing. Of course, in retrospect, if you look at this now, it looks ridiculous and silly, right? But again, it just shows you a very good example. When a new emerging technology comes out, there's a lot of hype. Did that mean that X-ray was just a scam? No, of course it's not. Again, it's a transformative technology. It just, when it was emerging, there was a lot of hype around it. So you cannot differentiate or tell the difference between what's the true value in it and what's the hype. So the point here is the same with AI machine learning. It obviously can do a lot of things, and I will give examples, especially for science, because the context here, we're speaking not commercial use of AI, that you probably have been exposed to when using chatbots and whatnot, or making images or whatever, or solving your homework at the university, whatever you use it for. But I'm speaking about the use of AI in science disciplines, right? To advance science and engineering. Again, there's a lot of prospect, there's a lot of hype. So I guess it's very early for this to settle down. You'll see more of it, but it's important to recognize that don't buy into the hype too much and it's going to do everything, and know there's limitations and there's useful, but also understand there's real value. And try the trick is to know exactly what this value is and try to push in that direction. So from now on, I'll explain a little bit about LLMs. Why? Not because I think they're foundation, and arguably you can argue even this is not the final form of models. If this presentation was 6 years ago, it would have all been about convolutional neural network, which is another type of model that is still a pattern recognition model. It just people found out a model that does better. But maybe in the future, and this is likely to happen, other types of models come out. That being said, if you understand how one model works, you can understand how the rest works actually. But being that LLMs is the, let's say, prominent model now, people are using it for many things, I thought it makes sense to discuss it. LLMs now are complex. There are several variants. Focus on text example, but give also how it can be used to process any type of data. And I use a running example, something called decoder only. There's a big family of models, but I'll use a traditional model you actually use yourself when you go to use ChatGPT or Gemini or so. I will focus on the exact model that is used there. So what is a transformer? Which is basically a model that is the technology behind large language models. Think of it that, again, we said a machine learning is basically mapping some input to some output. That's it. What did it choose to represent as an input? Sequence, and the word is called tokens. A sequence of small data bits, small parts of data. A good example, if it's language, you can imagine that each word here is like this sentence here. If you break it down into word by word and call each word of them a token. So the sentence was, it looks small outside, but quite big inside, whatever. And what you want to do is to learn the correlation. Which word is affected by which other word, and which other words affects me. So it's like a, kind of a brute force pairwise between each pair of them, right? That being said, people since then have moved on, and they thought, well, if a model at the end takes a sequence of inputs and predicts something, by the way, in language, it happens to predict the next word, right? But people thought I can use it for something else. I can use it for images. Images are very important for us, not only text. I can just take an image, split it into patches of pixels, put them in one line like this, and now your input to the model is just a series of tokens. It's just that tokens here where each token was a word, if it's text. If an image, each token is a patch or a box of pixels. Right? Okay, so if transformers was made for processing language initially, as I said, they now evolved to process any type of data that you can split into tokens. But let's go back to the basics. If you want to model or understand language, what would you do? A model language. A very simple example, I say, I want to model the relation between words in a language, right? I can say, that's easy. Pick a timeline, like a number line, just one dimension, and package the words together based on some property that are close in meaning. So for instance, I could say bird and horse and human, they're live forms. So I pack them together and give them a number, just some number. The exact number is not important. It's just that they are close. They have a similar number, right? I can take on very far from that, give a very different number, like 100, for example, or 200 or 500, and you have plane and car and train. They're not life form. And you can put virus and bacteria in the middle. I don't know, I'm not biologist or a life scientist, but you can argue that these are closer or somewhere in between here and here. They're not exactly here, they're closer maybe to this side, but they're of course always in like this. This is one way to represent words, right? The closeness in meaning is a living thing. If you're a living thing, you're on the left. If you're not, on the right. And if you're something, you can argue, put it on a number. Does the number matter? It doesn't matter really. It could be 20, 30, 25. It's just you're grouping basically based on some property, right? That being said, there's an issue here. This is a very, this representation of words only groups words by one property, right? But what happens if there's different property? That is, you say, well, I want to also group words but by different properties. Like one of them, I'll make, instead of one dimension I show on the previous slide, I'll make it 2 dimensions like this. On the x-axis, are you a living thing or are you not? On the y-axis, can you fly or you can't? So while human and horse and bird on this x-axis have the same number, like 10, 10, 10, but when you look at the y-axis, they're far from each other. Because a human and a horse cannot fly on their own, a bird can fly. Right? And similarly here. Okay? So what this, if you're if you work in physical sciences or engineering or math and so on, this is you probably, even if I mean from any field basically, because this is basically stuff you take, I think, what, junior high school? It's a vector space, they call it, right? It's just vectors. It's a very like Cartesian space of x and y. Each point in that space has 2 values, like the x-axis value, like the value you get on the x-axis, the value you get on the y-axis. And now I can represent each word by just a vector of 2 numbers, right? Okay? Now, me, because I know these words, I can put them here. But the question, can you make a model learn this? Well, we can. We can just start spreading them in random places. So now, randomly, each one of those has 2 values, one on the x-axis, one on the y-axis. But can the model learn on its own, right? It could. Think of it. And can I even not mention to the model what they're close to in? Can the model keep on seeing a lot of text examples to have these words in its own figure the correlations, right? What happens to come together, right? Can the model figure out some closeness in meaning and some closeness? I don't even know what it is. But basically, I want the model to take these words in this vector space and start to have words that are closer, in the same dimension together, right? You could. And your network, exactly a transformer is doing that, basically. It is actually moving these in training steps one by one until in the final step, it gives you, a spread out of these words in that vector space. This is exactly what a transformer or a large language model is doing. You don't see all of that. That happens in training time. That is when the model is learning language, right? And one point though, this is a simple example. I showed 1 dimension, I showed 2 dimensions. But words can be close, in meaning in one thing, but different in different things. So 2 dimensions is not enough. In practice, how many dimensions you need? This is from some models. You probably use some of them. DeepSeek, Llama, GPT. It's 4,000 dimensions. So now each word, or it can be 16 or 7,000. Like there's usually thousands of them. So that means each word. So if you're using Llama, that means it's a 16,000 dimensional vector. So each word is represented by a long vector of 16,000 values. At each vector position, there's one aspect or one property of the word, right? We call this the word embeddings. Right? You usually hear this word a lot, embeddings. What are embeddings? Embeddings are representation of each word in a continuous vector space, right? Is there a theory for that? No, at all. If anything, early stage models started with a big number because you would intuitively say, well, the bigger the number, the better, because there's many different ways the words can relate or correlate to each other. But over time, People realize, no, we have a lot of it. The model starts to learn like correlations that are not real, are not grounded in the actual, rules of the grammar of the language. Then they went down. Then they went up again. So it's purely empirical, basically, right? So there's no theory for the idle dimension for that. Okay. So as a reminder, embeddings is basically representation. I remove now the word or token and put data, because as a scientist, you can imagine this is the same, but instead of a word, it can be any data you have as input. Part of an image, or you can have an audio and cut it. If you're using EEG and ECG, you can think it's a signal. I can cut up this signal, discretize, and these are chunks of data. Whatever it is, it can be just any token or sequence of data. So it's a representation of data in vector space, right? And you basically want to learn that. So, number one, so what do you do for an LLM? Remember, we said in the beginning, any neural network is basically matching input to output. So the first thing you need to define is what the data you have, how do you represent it to the model as input, right? So first thing you do is you say, well, the model is doing something in a language, let's say English language. There's possibly 50,000 possible words. Right? It's probably more, there's maybe more, but they say let's limit ourselves to 50,000. Maybe in Japanese and Chinese, there's far less because it's more compact, it's pictographic, right? Then split the text into input of words. So if I write something like this, I can just cut it up. I can say one chunk is one word. And all what I'm doing is I have this lookup matrix where each word in this vocabulary, so you have a 50,000 words, possible words to use, a model can understand or learn, right? Each one of them has a vector representation, the one I told you about, 4,000 or 16,000. This represents the position of this word in a vector space, right? This is what you want to learn. You want to know how to group these words in a vector space, right? So the steps are as follows. So when you want to use an LLM, you give it a training text, corpus. Again, remember, this is an example on text, but it doesn't have to be text. It can be any input here. People moved on and generalized this. It can be any input data. It can be even continuous data that you discretize, or just data or pixels in an image, or part of a signal, or data in a table, anything. It could be anything. You split it into sequences. And then you do what you call tokenize. That is, it was a big chunk of text in this example. I split it into sentences. I took each single sentence, split it into words. So each color is one token now, right? And what I want to do is I want to make a lookup embeddings that each one of those possible words, like 50,000 of them, has a vector representation. I want to generate input matrices, right? And you want to learn that. I can skip this part. This is where it becomes very dry. This is a mathematical representation, but again, for completeness, I have it if you're interested.
How the tokens created? Because there, I saw the previous one. There, so terms of memory become one token, processing power become one token. But
excellent question.
Why
Surely
not
choose it? In fact, if you go to the site here, people come up with different tokenizers. That is, giving input, how do I cut it? Right? The very simplest tokenization for text, one word is one token. Very simple. Over time, people found, no, it's not ideal. Purely empirical, by the way. That if I split words in a different way, it's better to learn. There's a good example for that. Let's say I will use a model a lot for math. Right? You're a student, you don't want to do your homework. So you just give the model math questions. In mathematics, you might give a number in your text, right? How do I cut up a number, right? Do I cut it in the middle? No, you want to, But keep in mind that this is not dynamic. Once you decide and make it, it's done. You cannot change it. Once you make up your vocabulary of possible words, you cannot. So it depends on your task. People have figured out different tokenization schemes or tokenizers. There's some of it is grounded in statistics. That is, you see statistical occurrence of certain words, and they encode it based on how frequently a word comes. Some of it is based on like the theory of language itself, right? Some of it is based on, what's better when you compute from the efficiency point of view. In fact, if you go to this site, it's very amusing. You can give it any sentence, and you probably find a list of 20 or 30 tokenizers. And each tokenization scheme will cut this in different ways. Some of them are very amusing. They cut the word in the middle, actually. You cut part of the word, right? So I hope that answers your question. So again, here's where it becomes a little dry, and it's internally just mathematics. We're multiplying some matrices, so I can skip, but it's here for those who are interested. Okay? So this is, I guess, is the best maybe summary. So when you have an LLM, all what happens is you have a training data. Where does it come from? All the data they collect from the internet, from databases, and so on. You can then tokenize it. Again, in that example, it doesn't have to be text. It could be an image. It could be audio. It could be video. It could be spectral measurements from an instrument you have in your lab. But let's say it's text for this simple example. You tokenize it. You choose a tokenization scheme. And then your model takes representation of each one of those tokens now is sits in a vector space. It has a value in this vector space, high dimensional vector space. And all what your model layers are doing, they call them layers or blocks, are changing those values. So remember the animated example I gave you where the words are moving until they find the best position? This is what the model is doing for you. Until at the end of it, you had a sentence like this. You want to predict what is the next token, one token only. Right? So that means all your models, your LLMs you're using, is you even call it autoregressive. Autoregressive is just a fancy machine learning term to mean that it's a model where it predicts one thing only and the input gets back as, the predicted token comes out here, gets added, and then you go again. So if you give a model a sentence and it will generate 10 words, it doesn't generate the 10 words at once. It generates only the first word. And then the original text plus this word goes again as input. It's like a loop. And you generate the next token. And then you take that next token, append it. And each step, your input is increasing by size +1, +1, +1. So the model is predicting one token at a time. It's actually very impressive that LLMs kind of work when you're predicting one token at a time. Think of yourself as a human. If I ask you a question now, like you asked me a question, you have the thought in your head. And as I speak, I'm basically choosing which words to communicate my thought to you. These models are not like that. They only predict one token. They do not see the future. So as if I ask you to answer something, but when you're answering, you're saying word by word, and every single word, you have no idea what will come after it. Zero. You don't organize a thought, and then from that, or a plan, and then just choose the words to communicate. No. You only answer by giving one word at a time, and you have no idea what is the next word that will come. And then you spit out the next word. And then you look at the original question, plus the word you predicted, and then you give the next one, and then the next one. Again, very impressive that this works at all, right? And I guess the big finding, or the main lesson people learned, even in the space of AI, that not that AI models are smart or intelligent. It's just that the language is so regular, has very strong underlying patterns in it, that even when a model predicts, I'll just say this sentence. Even when a model predicts one token at a time, that is enough for it to generate something that makes sense.